Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. Today we are going to study about foundations of machines resting on elastic pads. These kind of foundations, they are relevant when the machine is to be supported on rock or concrete floor below. Now under such conditions, the stiffness of the underlying medium is infinitely high. As we have already learnt from the concept of transmissibility, when such situation arises that the machine is directly resting on rock or concrete floor, the transmissibility is likely to be over 100%. So this will stay more than 100% for all values of R, or the frequency ratio up to √2. Such a machine would transmit very high degree of vibrations in the surroundings. That's why it's very pragmatic to introduce elastic pads below the machine, so that the system has a reasonable value of stiffness rather than infinitely stiff. So what this does is that it reduces the natural frequency of the system, thereby increasing the value of the frequency ratio R. So we prefer that R should be raised above √2, and preferably if the value of R is greater than 3, then transmissibility would be less than 10%, irrespective of the damping. So let us analyze such a system where the machine is not resting directly on the concrete or the rock, but there is an elastic pad in between the two. So we need to work out the various stiffnesses of such a pad. So today we'll learn how to obtain the stiffness Kx, that is the horizontal stiffness, Kz the vertical stiffness, and K theta y the bending stiffness of the elastic pad. The horizontal stiffness in the y direction shall be Ky, and that will be similar to Kx. With the coordinate system as drawn, there will be another bending stiffness k theta x also that corresponds to pitching. K theta y corresponds to basically rocking. And then we also have a stiffness k theta z corresponding to yawning. Let us begin with the determination of vertical stiffness. We have already studied for the case of the rubber pads that the vertical stiffness is a function of both the Young's modulus and the bulk modulus of elasticity, and there are other parameters also. However, for the simple case where the bulk modulus is very high as compared to the Young's modulus, we have a simplified expression. So this particular expression is valid when the thickness of the pad is less than the lateral dimensions. So this expression can be finally simplified into EA by H. So this is same as that of the axial stiffness of a typical structural member under the condition that the value of the thickness is of the same order as the lateral dimensions. We have already done an exercise comparing the exact expression with these two approximations, and you should be now in position where to use which expression. Let us now derive expression for horizontal stiffness Kx or Ky. Let us consider the machine resting on an elastic pad of thickness h and plan area A, and let it be exerting a force in the horizontal direction as shown. Under horizontal force, the elastic pad will undergo shear deformation as shown here. So here the shear strain gamma undergone by the pad plays an important role. We know very well the relationship between shear stress and the shear strain with the shear modulus of elasticity. So we'll use this expression to derive the expression for the horizontal stiffness. So expressing the shear force as ratio of the applied horizontal force to the plan area and the shear strain as the ratio of the horizontal displacement at the top relative to the bottom divided by the thickness of the pad, we can derive an expression for the horizontal stiffness Kx. Because the horizontal stiffness Kx basically relates the applied force with the horizontal displacement delta. Therefore, the expression for the horizontal stiffness Kx is Ga by h, and same expression holds true for the stiffness in the other direction, that is the y direction. Let us now derive the expression for the bending stiffness k theta y or k theta x. For this case, we consider the machine to be resting on the elastic pad and exerting a pure bending moment My. As a result, the deformation produced in the elastic pad is that of bending deformation. At any instant of time, this would be the shape of the pad. Now here we'll apply Euler's bending theory to derive the expression for the bending stiffness. Let 2a be the length of the pad and let the vertical deformations at the extreme fibers be delta naught as shown here. The corresponding angle of rotation is represented by theta y as shown here. Delta naught and theta y are related as shown here. We begin with writing the expression for the tensile or the compressive strain at the extreme fiber. Then we express strain in terms of the stress and the Young's modulus. once we have stress, it can be written in terms of the bending moment My, the corresponding moment of inertia Iy, as per Euler's bending theory. And once we have this relationship, we can just do algebraic manipulation and obtain an expression, a closed form expression for the bending stiffness of the elastic pad. So basically this relates the applied bending moment with the angle of rotation. So in very simple terms, the stiffness k theta y is basically E multiplied by Iy, which is the corresponding moment of inertia, and the product being divided by h. So this is k theta y. Similarly, we can write expression for k theta x, but in that case we have to substitute Iy by Ix. Lastly, we need to derive expression for the yawning stiffness, that is k theta z. So taking cue from the previous derivations of the stiffness is kx and k theta y, we can directly write an expression for the yawning stiffness, which is also denoted by k phi or k xi as gj by h. So here j is not the polar moment of inertia, but it is the torsional constant. So if we can refer any solid mechanics book, and we can obtain the expression for torsional constant for any particular shape. Earlier, when the foundation block was considered to be resting directly on soil, we were using the polar moment of inertia for simplicity. However, now, because we have a rubber pad which has more defined engineering properties, so we can use more accurate expression involving the torsional. Let us now extend the discussion to group of elastic pads. Usually, it is not practical to place a single very large sheet of rubber below a machine. So usually we place an array of elastic pads, because rubber pads are generally available in small sizes which can be adjusted, and usually these are placed at the anchorage points. So we may use a set of 4 pads or 6 pads or 9 pads, or similarly any other number of pads as per the availability of the anchorage points and our requirement. So in the present discussion, we are assuming that all the pads, they are identical and they are symmetrically placed. So we begin with the expression for vertical stiffness. In the case of the vertical stiffness, basically the stiffness of a group of n pads is simply the stiffness of a single pad multiplied by factor n. On similar lines, expression can be written for the horizontal stiffness in the x direction or y direction. So here we simply multiply the stiffness of the single pad by n. Now coming to the bending stiffness, the expression for bending stiffness is basically I of the entire group multiplied by E and divided by the thickness H. Using the concept of solid mechanics, we can find a simplified expression for the moment of inertia about y-axis of the entire group. So here basically we use parallel axis theorem and we transform the moment of inertia of each pad about the centroidal axis of the entire group. Now in this particular situation, taking advantage of the small size of each pad, we basically ignore the moment of inertia about its own centroidal axis. So that gives us a simplified expression for the moment of inertia of the entire group. So all we have to do is just do sum of squares of the x coordinate of the centroid of each of the elastic pads, and this sum has to be multiplied by EA by H. So basically we are expressing the bending stiffness in terms of the vertical stiffness Kz of each individual pad. Similar expression for k theta y can also be written. Now after this, it should not be at all difficult to derive an expression for the yawning stiffness, that is k theta z of the group, which is also denoted by k phi of the group or k xi of the group. So it is basically g multiplied by j of the entire group by h. So here we can use the parallel axis theorem, and what we find is that this expression is given by g a by h, which is basically kx, and this is multiplied by summation of ri square, that is the radial distance of the centroid of each of the pad with the centroid of the group. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.